Mechatronics is a natural stage in the evolutionary process of modern engineering design. The development of the computer, and then the microcomputer, embedded computers, software advances, made mechatronics an imperative in the latter part of the 20th century. In this short video we will be discussing basic definitions, key elements of mechatronics, industrial scope and what's next. The definition of mechatronics has evolved since the original definition by the Yasukawa Electric Company. The word mechatronics is composed of mecha from mechanism and the tronics from electronics. In other words, technologies and developed products will be incorporating electronics more and more into mechanisms, intimately and organically, and making it impossible to tell where one ends and the other begins. Another definition was presented by Hirashima, Tomizuka, and Fukada in 1996. According to them, mechatronics is the synergistic integration of mechanical engineering with electronics and intelligent computer control in the design and manufacturing of industrial products and processes. Shetty and Koch in 1997 define mechatronics as methodology used for the optimal design of electromechanical products. And Oslander and Kempf suggested mechatronics as application of complex decision-making to the operation of physical systems. W. Bolton defined the mechatronics as, not just a marriage of electrical and mechanical systems and is more than just a control system, it is a complete integration of all of them. Now let's talk about the key elements of mechatronics. The study of mechatronic systems can be divided into the following areas of specialty: physical systems modeling, sensors and actuators, signals and systems, computers and logic systems, software and data acquisition. As the field of mechatronics continues to mature, the list of relevant topics associated with the area will most certainly expand and evolve. Mechatronic engineers can work with electronics and mechanical systems together and solve problems that cross discipline boundaries. The list also includes electromechanical components, computer science, mechanical components, electronics, electronics software, software for mechanical components. Mechatronic engineering is the engineering discipline concerned with the research, design, implementation and maintenance of intelligent engineered products. Industrial scope of mechatronics. Some of the expert areas which mechatronics engineers can utilize: artificial intelligence, control system, data communications and networks, dynamics of machines and mechanisms, human-machine interface engineering and ergonomics, industrial automation, process management, optimization, and control process, plant and manufacturing systems, robotics, smart infrastructure. In the late 1970s, the Japan Society for the Promotion of Machine Industry (JSPMI) classified mechatronics products into 4 categories. The enabling technologies for each mechatronic product class illustrate the progression of electromechanical products in stride with developments in control theory, computation technologies, and microprocessors. Class 1 products were enabled by servo technology, power electronics, and control theory. Primarily mechanical products with electronics incorporated to enhance functionality. Examples include numerically controlled machine tools and variable speed drives in manufacturing machines. Class 2 products were enabled by the availability of early computational and memory devices and custom circuit design capabilities. Traditional mechanical systems with significantly updated internal devices incorporating electronics. The external user interfaces are unaltered. Examples include the modern sewing machine and automated manufacturing systems. Class 3 products relied heavily on the microprocessor and integrated circuits to replace mechanical systems. Systems that retain the functionality of the traditional mechanical system, but the internal mechanisms are replaced by electronics. An example is the digital watch. Finally, Class 4 products marked the beginning of true mechatronic systems, through integration of mechanical systems and electronics. Products designed with mechanical and electronic technologies through synergistic integration. Examples include photocopiers, intelligent washers and dryers, rice cookers, and automatic ovens. Mechatronics, has evolved over the past 45 years and has led to a special breed of intelligent products. For some engineers, mechatronics is nothing new, and, for others, it is a philosophical approach to design that serves as a guide for their activities. Certainly, mechatronics is an evolutionary process, not a revolutionary one. Sensing and sensor fusion will be the next capability to be acquired by mechatronic systems. Already, many mechatronic units possess rudimentary sensing abilities. For instance, modern air conditioning units are able to sense air temperature and humidity through separate sensors and fuse the signals through fuzzy logic reasoning. Sensors produce copious amounts of data that need to be digested to discover patterns of interest before control can be effected through the actuators. Intelligence means adapting to the environment and improving performance over time. Within the domain of mechatronic engineering, there has been considerable interest in learning through the use of artificial neural network and fuzzy logic for applications in control and robotics, autonomous guided vehicles, etc. that require mainly reflective intelligence when performed by human operators, and tasks, such as machine diagnostics, requiring combinations of reflexive intelligence and low-level reflective intelligence. This interest will continue well into the future. Autonomization refers to the development of the ability to survive and perform robustly while the external environment changes. With progress in sensor unlearning technologies, tomorrow's mechatronic devices can be expected to become progressively more autonomous. They will be able to reset their local goals autonomously under changing external environments, so as to meet the broad system-level goals set by human beings. Miniaturization refers to the trend towards mechatronic units of significantly smaller size. Progress in precision engineering, newer materials, composites, diamond coatings, etc., and nanotechnologies will contribute to this development.